EpiPatch is a seizure detection and classification device. The primary user is the caretaker of the patient. From research, most caretakers fear missing out a seizure episode as it can be detrimental to the patient's health. Our device can be worn as a patch on the patient's body during unsupervised activity. The device will continuously monitor the patient's vitals and movements. When an episode is detected, it begins timing the seizure while the caretaker receives a prompt alert with seizure aid guidelines and a direct line to their preferred emergency services. As makers of an AI system, the device aims to only supplement a diagnosis. While all information collected during the episode can be accessed and evaluated by a doctor for further tests. In this scenario, the patient is sleeping while the caretaker is awake. EpiPatch here is worn and detects the seizure that occurs during this nocturnal episode. The information is immediately sent to the companion application to alert the caretaker of this event. There is immediate guidelines and a line to an emergency service for their use. The patient's data is recorded in the application, which can be viewed by the medical professional to make a sound judgment about the patient's condition.
The figure here shows the high-level architecture of the proposed system. The proposed system aims to provide an accurate and reliable seizure detection system for epilepsy patients. The device consists of a wearable patch that is placed on the skin, which contains multiple sensors that continuously monitor the vital physiological signals of the user. The data collected by these sensors is then processed by an AI algorithm that is trained to recognize patterns associated with seizures. In the event of a seizure, the algorithm activates an alarm to alert the user or their caregiver. The device is designed to be non-invasive and comfortable to wear, allowing the user to go about their daily activities without any interruptions. The patch is small and lightweight, and the sensors are placed in a way that does not interfere with the user's movements. This makes it ideal for long-term monitoring, as it does not cause any discomfort or inconvenience to the user. The AI algorithm used in EpiPatch is based on deep learning techniques, and it is trained on a large dataset of physiological signals collected from users. EpiPatch includes multiple sensors, including accelerometers and biosensors, to measure and record various physiological signals such as heart rate, blood pressure, and SpO2. The biosensor we used was a MAX 30102 sensor, and accelerometer was one built in the Arduino Nano 33 BLE Sense as seen in this figure. The data from these sensors is used to identify patterns that are indicative of a seizure, and then the collected data is processed in real time to extract relevant features and detect seizures. A machine learning algorithm is trained on large amounts of data to recognize the patterns that are indicative of different types of seizures. We tested the hardware components throughout every step of the design to ensure that they are working properly and won't affect the final results of the device. The PCB design of the EpiPatch is crucial for its functionality as a seizure detection device. The PCB design integrates various components including microprocessors, sensors, and wireless communication modules into a compact and efficient form factor. Our proposed system uses a multi-layer PCB design with each layer serving a specific purpose. The top layer is dedicated to the placement of the sensors, which are responsible for detecting seizure activity. The sensors used in the EpiPatch are highly sensitive, low power consumption devices that are optimized for seizure detection. The second layer of the PCB contains a microprocessor which is responsible for processing the signals from the sensors, detecting seizures, and transmitting the data to the external receiver. The third layer of the PCB is dedicated to the wireless communication module, which enables the EpiPatch to transmit data to an external receiver in real time.
As we can see in the mobile application, the first image shows that the caretaker received an alert. The second image shows how the caretaker can help someone who's having the seizure. Third image shows the type of seizure the patient was having. Moving on to the mobile application and artificial intelligence configuration. The mobile application is a crucial component in our proposed system. It provides patients and caretaker with convenient way to access information and manage the device. The application is designed to work seamlessly with EpiPatch device, allowing the user to access important information and adjust the device setting from their smartphone or tablet. The mobile application is divided into 3 sections. The first section is seizure monitoring. The application provides real-time monitoring of seizure detected by EpiPatch device. Patients and caretaker can view information about the type and the severity of the seizure, as well as the time and duration of the event. Second is the alert. The application provides an easy way to receive and manage alerts from the EpiPatch device. In this event of a seizure, the application will provide an alert with relevant information, allowing the patient and the caretaker to respond quickly and appropriately. Lastly, the user-friendly interface. The application is designed to be user-friendly with simple and clean interface that makes it easy to access information and manage the device. As we can see here in the video, for the AI testing, we have successfully gotten the AI to conduct classifications with vital signs monitoring. Therefore, artificial intelligence for seizure classification is a common manifestation of epilepsy and can present a variety of forms, each with its own characteristics feature. There are several different types, including tonic-clonic seizure, absence seizure, myoclonic seizure, and many more. In our proposed system, we used artificial intelligence to classify the different types of seizure based on their distinctive motion. Using mobile net architecture, we train our model to recognize and accelerometer data of distinct seizure. The algorithms are planned for deployment on Arduino with an accelerometer sensor. After testing, the accuracy of our algorithm is 93% with sensitivity of 89%. The speed of seizure detection is an important factor in ensuring that the individuals experiencing seizure received prompt and effective treatment. The results of our evaluation show that EpiPatch was able to detect seizure in real time with median detection time of 5 seconds.